Today we're going to see the different kinds of controls that exist and what each one does, and we're going to see how we implement the control systems on the physical systems that we already have. So in here we have as you can see on the screen in here, some magician in there. We're gonna do our magic here to understand what control systems are about. So let's move down, and here we have control systems as a whole, and I entitled like computer design of feedback control systems, meaning that we are going to be using our tools, software tools, to do this. You have two kinds of control systems. That's the first sort of easy classification. Ones are called open loop controls, and the other ones are called closed loop controls. Okay, so we're going to see examples of each one of those. Here's the basic concepts. Of course, we would like to use our software to design. And what is a control system? What does it actually do? The purpose is to adjust or to regulate the flow of energy in some way that you want. You want, let's say, the temperature of this room to be 68 degrees. Well, you set the thermostat to 68 degrees, and what you have done is adjust the flow of heat, energy in the form of heat, to that temperature. And how do you control it? That is what we're going to be learning. Closed loop control uses measurements so that you can modify the output depending on what you measure. Best example, the cruise control of your car. You set it to 65, and if you're not doing 65, the car would automatically accelerate a little bit or would slow down. This is a closed loop control system because it has a sensor that tells the controller how fast you're going, and depending on what you're doing, it adjusts either up or down. The open loop control system does not use feedback. It adjusts the flow of energy on a schedule. For example, typical control system, Christmas lights. They turn on at 7 in the evening and turn off in, wherever you set up that timer. The irrigation systems, the watering your lawn, it has a little clock in there where you set up how long the water will be on. Also the ovens, for example, you set it up for a timer, right? So that the turkey is well done or done in 3.5 hours. Or if you want to heat something, of course the examples of this are also the different kinds of ovens that we have, even microwaves and other things like that. So just to give you an idea. What is automatic control? Automatic control acts without the sudden intervention, and it requires the system that will require an operation. So it can be either closed loop or open loop, of course, because for example, the newer cars have a setting where, depending on how dark it is, automatically the lights come on, right? So it's an automatic system. And you have many things that work like this. We, as you have seen previously in this class, we do a lot of things by building computer models of real life, of real things. So what we do is to simulate how the system is going to behave, and of course we would like our model to be as close to reality as possible, and depending on what it does, we will adjust accordingly to do the calculations. This is perhaps the most important picture that you need to learn, because it shows all the possible components of a control system. What is interesting here is that in this situation here, you have the control system, the physical system here. This GP is the physical system. In control systems, they also are, we know it as plant. The plant, whenever you hear about the plant, it means that you are talking about the system that you want to control. Okay? Then you have all these other components we're going to go through. Okay? You have an output, obviously, from the plant. That is the control output, this CS. But at the very beginning, here, you have the input command. In other words, this is you going to that setting. I'm setting the temperature of what you want, or having the vehicle adjust to the specific speed that you have set it up. Okay. So after you do the measurement, that measurement signal goes through this so-called feedback element, which could be, like, for example, this box could transform the RPM that you measure from a motor here into a voltage here. And your setting here will produce a set voltage in here. That voltage, this voltage, or you could call it the reference voltage in here, would be compared to the one that you get from the system. And then the difference of this will produce an error. This is the error signal here. And what will happen is, after this obviously is a voltage, right? This has a control logic element that analyzes this error. And then with this, depending on what the error is, you are going to put in here the different control systems. See where it says final control right here? Okay. And then, depending on what the error is, you already processed that. The controller here is going to take an action to modify your system. But the problem is that we have to accommodate the fact that, despite the fact that the control system tells the plant what to do, in the case of the temperature, for example, somebody opens the door, or if you are controlling the temperature inside your refrigerator, the fact that you open the door messed the temperature up. And that event is called a disturbance. So what happened is that this again, the disturbance in here is acts on your system, and what the system ends up getting as in the form of a control signal is the difference between what the control wants it to do and this disturbance signal. And so you see, you might not get the total control that you want, and this output is going to be messed up. But it takes another measurement and it goes through the same cycle. Takes the measurement, goes through the cycle, overcomes this, and keeps going until it adjusts the the output the way it's supposed to be. Granted that, with this disturbance in here, we don't know if the disturbance is like constant or if it is just like somebody opened the door and then close it later. Obviously, you want to reduce this to 0. Two things you want to reduce to 0. This disturbance, but also this error. That's the whole objective in here. So, in all chapters, 2 and 3, up until now, we study this, our system. Now, we are going to mainly be concentrated over here on these ones, because that's where the most important part is. So in here we have this response. Let's say that if you put an input in here to test and you want the response in here, if the response is a curve like this, you have the time for the maximum is called the peak time, and this is going to be the signal as it would settle down. But you have some sort of a band in here before the system gets settled. But you see, if your objective was that the system would operate on this line and the system would settle over here, then you have produced what is called the steady state error. You see, and that's what chapter 7 deals with, with the steady state error. But the point here is that no matter what you do, something you will have to adjust. Either the system doesn't quite correct the error, or the system shoots up too high or too low, or it is too fast or too slow. So you see, there's all these variables that now we need to worry about to say what the system will do with the control. And our objective, like I said, would be to reduce the disturbances here, but also reduce the error. But how are we going to do this if I'm already telling you that in some systems we have the steady state error? Well, that is where the different kinds of controls come into picture. So we would like to minimize the steady state error. We want to minimize the settling time, and to achieve other transient specifications such as minimizing the overshoot. Do you see what I mean here? So in general, if we put like a test signal, like a step input, and we see all these things in here, we can say, I want to minimize the steady state error. I want to do better with the settling time, to be shorter or maybe longer, depending on what you're doing, and other specifications. We have like a 2-position control, which is like on and off controller. Is also called a bang controller. For example, temperature control is like that. You have a proportional control. We will study proportional control when your plant is a first order system, meaning it doesn't have a second order differential equation. It's a simple system. Or if we have a second order system, then we will have to deal with that. So right now I'm just outlining the different kinds of controllers. The proportional control means I am going to put a controller proportional to the error. So the more error, more control. The less error, less control. That's the idea. Okay? So there's another type of controller called integral control, and another one called derivative control. So right here in one slide, you have all these kinds of control systems, and we need to go one by one, studying each one of these and what each one does. So I will be giving you some examples of each one of these controls. For example, a two-position control system. Like in here, you have that this is like a float valve, for example. The thermostat. So you have the control. Depends on on a cycle like this. You know, it's either on, then, for example, the tank in the bathroom. You know, the toilet is typical in here. It needs to fill out a certain amount, and then the valve shuts off. Then it's used again, goes up, and then goes down. So this is the kind of control, two-position control. This would be like on and off controller, for example, in here. So there's a liquid level controlling here, so you have a floating in the air. As you can see that it has a supply of water, and this valve in here either opens or closes. Okay, so in here what will happen is when it fills up, you say disconnect this, so the valve is going to be you know, the solenoid will act this. But if this goes down, it closes the circuit, so opens the valve and then lets the water in. So how does it work? If this is time and this is the height of the tank, you know, you have this curve to fill it up like this. It will operate like this. But in reality, when you turn it on, it doesn't quite shut off automatically. It goes a little bit, and then it goes this way. So they're always a bit off, and the idea is to reduce this this error. So that's the kind of controller which would be a liquid level control system. Band control. This one operates either, the ideal would be it's in here off and then it's on like that, right? But usually it doesn't work like that. It has a bit of a delay, a dead zone in here, and it works like this. Okay. This one is very familiar to you. Thanksgiving, we do our turkeys here, and to make it perfect, you have to have a certain time and a temperature, right? But we never think about from the engineering point of view what goes on, and I'm gonna have you reflect a little bit on this. If this is the oven inside here, and you have the heating element in here, that heating element has to have a control system, okay? But you see, when it heats up, not only heats up inside, but also the walls. And if the walls are not insulated, then you lose heat. And you, instead of concentrating on the oven, you are sending it outside. So ovens have very good insulation to keep the heat on there, and that's what this is. So how does it work in here? You have a place where you put the, set the dial for what you want. And this power amplifier is the one that actually produces the voltage for the heating element. And also at the same time, depending on what the thermostat, the sensor does, this thing is going to shut it off. So this is the typical electrical temperature control. So in here you see you have, for example, you have a thermocouple in here. That thing has to produce a voltage. That we represent this with this kind of equation, because it has to have a gain and the temperature, right? And then you have in here the voltage from this potentiometer to either, to heat up this. And then you have this typical setup, with the power amplifier putting voltage for this and changing it depending on what the sensor does. In here, in the temperature controller of this, if we reduce it, we need to begin working and reducing the control loss to equations, like in this, for example, in this case, if it is a heat transfer problem that has this kind of differential equation, do you notice is dt dt? This one is a first order system, because the derivative that controls the behavior of this oven is only first order equation. So in this case, the control condition is that T2 should be constant. So if we look at the heater, Q of the heater should be equal to the lost energy. So Q, the steady state, would be the difference in temperature divided by the resistance. In the case of the amplifier, is to provide the heat for the oven, and also to compare the voltage coming from the sensor and coming from the dial that you set the temperature to. So the heater output is going to be this QSS plus M, which would be the control itself. Okay, so it depends on these values, how strong the control system is for this oven. In here, the temperature controller, you have T2 200 and outside 70 degrees. You also have the physical system equation, and you have the loss of the difference of the heat and the steady state. So these are the kind of things that we want to analyze, but now in more detail from the systems block diagram point of view. Here's what we can recognize. This is your system right there. Okay, you measure the variable in here, temperature in here gets transformed into a voltage that is compared to what you have originally set up. That comparison produces an error. That error in this case is a proportional control. In other words, you see this is a constant. The more error, the more control. and in here is the disturbance. So when you are designing a control system, like in my case, I will have to give you the conditions. What we want the control system to do. Because what's happening here is your plant, this is your physical system, is being modified by this other block. If between these two you have a transfer function, then the combination of the controller plus the system produces a different output, which is the one that you want for control system. Yeah. You need to design based on the time constant, I mean how quick the system is. The damping ratio, meaning does this system have a component that dissipates energy and how much? And then we have to worry about the natural frequency. The stability. Remember we talked about if a system has the poles on the right hand side, system is unstable. If the poles are on the left hand side, the system is stable. How quickly can it respond and how accurate it is. All these things are from our basic concepts of what we want to do, are the objectives of what on each problem and controls we need to decide. You can have this in a more practical way in here. If you have a position control system, for example, in here, you see, let's say this is the motor in here, and you have a flywheel that is turning here. In this case, you see this little gear measures it, the position of this flywheel. And this thing is going to tell us where it is, what the position is. If you feed back this to the amplifier here, and also you have the setup in here, you compare the two, and this device is going to command the DC motor to either increase the torque or decrease it. Do you see how it works? So your system being here is controlled by these two units here. So if you have the block diagrams of each one of these, you can see that what we have studied so far, this plant is the transfer function right here. This would be the feedback, gets compared with the reference, produces an error, and goes through this amplifier, and then that goes to this motor, which in fact is the actual control system. Okay, I already talked to you about the disturbance, and we try to make it 0, and if that's the case, what you're seeing, if we eliminate this, you have that the transfer function, which is this motor plus the system plus this logic, that is an overall transfer function of the system. So let's take a look the second type of controllers, the proportional control. I said this is the more control you have, the more error you have, the more control. In this case, the feedback signal is proportional to the error signal. So the more error, the more control. So the control signal is a proportional constant multiplied by the difference in the set point and the current value. This is another way of saying error. Set point minus current value, read error. So if you multiply the error times the proportional constant k, you will come up with the control signal. So if you have the DC motor in here, DC motor has a tachometer that measures the speed and position here, feeds back to the amplifier, which takes the difference between the value you set up and the actual value, and this error is corrected over here with this power amplifier and the DC motor. That is how it works. It's pretty simple. All you can see with the background that we have right now is a very small step to go from the transfer function of the system to the transfer function of a closed loop system, which is what you have in here. Sometimes if you don't have the ability to just do proportional control, there are two others that do different things, like the integral control, for example. It reduces the error and tries to reduce it to 0, but it has a problem. It oscillates too much. This one, proportional control, is the one we can put in here for this example using the motor, right? So you have the control system and the physical system with this proportional control. Let's try something a little more complex. You have in here the proportional control system. See? This is your system. This is the measure. Get your feedback in here, compare it to the original, produce the control system. And you will end up with this kind of equation. So you are obtaining the transfer function of the position with respect to the torque, or the position here with respect to the to this other input right here. You know that by now everybody should have totally and in your mind the idea that a transfer function is a relationship between the output and one input of the system. And that's what we are seeing here. This would be a transfer function between that output and this, or between this output and this torque. So that's how it works. So if you have the plant and the input is a step input, the step input can be simulated as 1/s. If you put the input plus the transfer function and you try to find out what the response is, you're going to see something like this. And then you can calculate what the value would be. So this is, we need to do some more exercise on this. In this case, for example, the change in the load torque, and you could model also as a unit step input in here, multiply by the transfer function of the system, and we calculate the steady state error. This is the thing that is in chapter 7 that we need to review. Summary of proportional control. First order system. The output never reaches the desired value. Its resistance is present, and although it can be made arbitrarily close by choosing the gain large enough, it is always with an error. So proportional control is very good, it's quick, but it leaves us with a steady state error. As the output approaches the final value without oscillations, the time to reach this value is inversely proportional to the control. So meaning the more control, the faster it's going to get there. So the output deviation due to the disturbance at the steady state is inversely proportional to the gain. And the error will always be present even in the absence of damping. So this is a problem. We have one set of control. We need to learn how to deal with this. We're going to study the other kinds, the integral control and all that stuff. So I am going to stop here, and we'll deal in our next video about integral control, so that we go step by step.